Hey guys, welcome to Unit 1A, Notes A. This is Chapter 11 in the IB textbook. In these notes, we're going to look at measurement and precision. So one weird reason why we're starting with Chapter 11 is because Chapter 11 focuses on something called uncertainty. We have to make sure that the measurements we take throughout the entire course in all the other units have an uncertainty with them. So we're going to start off with a basic understanding of what uncertainty is and how it affects our measurements. It essentially comes from how reliable the tool being used to make the measurement is. So when we record our measurements, we want to pay attention to which numbers are known, what are the meaningful numbers, and which numbers are estimated. This kind of relates back to our significant figures rules. What made a number significant or not was whether we were able to actually reliably measure it or not. So this goes back to the tools that are actually used. You would go to as precise as you could, whatever the markings were on the instrument, and then you would make one further estimation. And that would be as close, as reliable, as precise as we could get. And that was our significant figures rules. So it does include one estimated digit, and that's essentially the crux of where the uncertainty comes from. That estimation, that uncertainty in an estimation. So I want to start with a quick recap on what the significant figures rules were, basically. A non-zero number would always count as significant. It's only the zeros that we have to be careful of, and essentially the idea is that placeholder zeros are insignificant. It's only the zeros that are actually intentionally measured that are significant. So a couple basic ideas here. If the zero's in front of a number, like with 0.05, this would count as decimal present, and so we would start from the Pacific side, or the left-hand side of the number, and just count the 2 and the 5. We would basically go through those zeros, having two significant figures. If the zeros are in the middle of the number, no matter which way I start counting from using the Atlantic Pacific rule, I'm always going to include those numbers. So in this example, there is no decimal, so we would think of this as decimal absent. Even if there was a decimal at the end of it, you'd start counting at the 9. Either way, those zeros end up as significant. So this would have all 5 significant figures. Where it gets a little bit tricky is the trailing zeros, the zeros at the end. So it really goes back to the Atlantic Pacific rule. So let's look at this example here, 120. Without the decimal, we would consider that decimal absent and follow the Atlantic rule, counting only 2 significant figures. But if you took that same number and you put a decimal at the end, now being decimal present, we would start counting from the Pacific side and count all 3 significant figures. You would still do this even if it is a decimal present, if there's no numbers in front of the decimal, and my first non-zero number is after the decimal, then that's where I start counting. So that would end up with 4 significant figures. So you got to be careful with the trailing zeros and apply your Atlantic Pacific rule. But if it's in front like this, decimal present, we ignore them. Captive, always include them. And if it's not a zero, it's always significant. That's your basic recap on your significant figures rules. You also want to be careful when you use those numbers in calculations that you're also applying the significant rules for calculations, because you never want to end up with an answer that's more precise than the measurement that you started with. So the rules in place for that are different whether you're dealing with multiplication and division or addition and subtraction, 2 main different categories. So if you're dealing with multiplication and division, then you're going to go by the least number of significant figures of your factors. So here I have 3 significant figures versus 2, so my answer should end with 2 significant figures. For addition and subtraction, you actually go by the least number of decimal places, which kind of makes sense if you look at it lined up, like when you first learned in grade school. These would be assumed zeros here, so that's not precise, that's not good to use in our final answer. We would want to make sure our final answer has the least precision of one of our factors, so 1 decimal place for the answer there. Always making sure that you have your answer limited to the least amount of precision of whatever measurement is being used. Your final answer cannot be more precise than the measurements used to get there. That's the main idea on calculations. The idea here is your calculator, when you calculate things, is going to give you lots of numbers, and then you have to consider the precision of your factors and limit the number of significant figures, and in a little bit also the uncertainty based on the tool. So you're going to have to kind of police your significant figures for yourself. So the significant figures are based on our instrument. Now, how does this tie into uncertainty, our big new idea for chapter 11? So let's look at an example here. This tool that I have over here is called a burette. This is used for titrations. And remember that the 0 is at the top, indicating 0 milliliters of titrant had left the burette. In this case, we have dispensed some titrant. And so let's zoom this in a little bit. We can see kind of where the level of titrant is. Remember, the numbers are backwards with 0 being at the top. So I can tell it's between the 20 and 30, even in my non-zoomed in one. And then if I looked at the zoomed in one, I can tell if this is 20, that would be 21, 22. And I'm dipping just a little bit below the 22. So I know it's between 22 and 23, but I need to estimate one more. So I have ones place markings on my burette. I can then estimate the tenths place. It's not right on it. It's not quite halfway down. That estimation is a 2. Maybe you would estimate it at 22.1 milliliters. That's valid as well. And that's where the idea of uncertainty comes from. Is it the 0.2, 0.1? That's kind of up to interpretation, right? And so that makes it a little uncertain. All right. Let's look at this with a ruler. Let's do some practice on our own. So looking at this ruler laid up against this blue bar, I can tell that I'm between the 3 and the 4. So using the markings, tenths place markings, what would be the number that I would record there? So I would record the 3, because I know it's greater than 3. The marking seems to be on the 5th marking, so I know it's 3.5. But I can actually visibly tell that it's exactly on that 0.5. And so then I would estimate the last number as the 0. Maybe you think it's a little bit further than the exactly on the 5. And so you would estimate the last one as 3.51. Either way, we're limited by the tool with one estimation. That's how recording data works. So the precision is based on the tool or the instrument that's being used, which means we can also look at provided data and then interpret what the precision of the tool was. So let's do an example of that. The question here is, how precise is a graduated cylinder given that this was my reading? In this case, since I have a tenths place, that would be the estimate. That would be the one that I looked at its relation between the 27 and the 28, and I decided it was halfway down. So that means the ones place would be the marking. Ones place would be the marking on the actual graduated cylinder. So this graduated cylinder had a precision of, or markings for every one. Like maybe it was 27, 28, and then we were able to estimate the 0.5. So we've got to be able to look at given data also and reflect on the tools that were used or the instruments that were used. All right. So there's a general understanding, and I would agree for the most part, that being more precise is better. Of course, we would want as precise as possible, right? But there can be a drawback. So let's look at another example here. We have a graduated cylinder that has 1 milliliter markings or ones place markings. But then we also have a pipette which has 10 marks per milliliter, or 0.1. It has markings to the tenths place. So which would be more precise? Well, by definition, kind of having more decimal places would allow for greater precision. So the pipette is absolutely more precise. So what in the world could be the advantage of a graduated cylinder with 1 milliliter markings? Well, if I wanted to measure 50 milliliters of fluid, I wouldn't want to use a pipette that could only handle maybe a milliliter or 5 milliliters at a time. I would have to use that pipette way more times in order to accurately measure out 50 milliliters. And then that would just compound the uncertainty. It would make it worse because the uncertainty would pop up every single time you do a measurement. So you've kind of got to balance using a tool that's fit for the volume that you're measuring and using the most precise tool for that job. A burette can actually handle 50 milliliters and it's very precise. So ideally that would be what we would use if we wanted a very precise measurement that contained 50 milliliters of stuff. But you if you don't need 50 milliliters, if you only need a milliliter, maybe we can use the pipette, and maybe that's more precise. So there are advantages for either one, and you've got to think about it for every single lab. What's the most precise glassware that's good for the job? So looking at the pipette, kind of a more quantitative approach, just so you can see how this looks. If the pipette has tens place markings to the tens place, then we can estimate that last digit. And the uncertainty would have a matching number of decimal places here. So this is what I'm trying to point out. The magnitude or the decimal place, the place value of the uncertainty should match. Whereas if the graduated cylinder only had ones place markings, we can only estimate to the tens place, and the uncertainty would also have a value to the tens place. We're going to describe in just a minute where these actual uncertainties come from, how to calculate them, but for now I want you to see that there should be a matchup. Whatever the uncertainty is should match what the significant figures are for the measurement. One trick here is that this only applies to the measurement. So sometimes I see a common mistake where after calculations, there's not a matchup, and that's okay. And that tends to freak people out because the general idea when you take a measurement is that it should match. But just like with significant figures, it might look different after a calculation. Just keep that in mind. All right, so we're looking at precision here. We should probably make sure we know what precision is as opposed to a commonly confused term, accuracy. So precision is how close together the numbers are, how closely they agree with each other. This is going to essentially tell us if I did the experiment again, would I be getting the same value? Is it reproducible? Is it agreeing with each other? How close together are the numbers? And decimal places play a role here because they help us tell how close together the numbers are. For example, 24 and 25 sound close together unless I ask you to compare that precision to numbers 24.5 and 24.6. Well, those numbers are much closer together. And how can I tell that? Because they have more decimal places. So the decimal places do essentially mean more precision because we can then tell how agreeable those numbers are, how close together they are. Just because numbers are precise or close together, though, does not necessarily mean you got the right answer. It does not imply accuracy. So the definition for accuracy is basically, is it right? How close is it to the true value? And this is something we can evaluate using percent error. The catch is, if I don't actually know the true value, it kind of makes it hard to evaluate the accuracy. Got to kind of pay attention to that. So this little graph, or image should look a little bit familiar. This is essentially a visual way to describe and compare accuracy versus precision. It's the same thing from our Honors Chem notes. Accuracy and precision are both low in this picture, because you can see that none of these dots are really on target, so they're not accurate, and they're not really close together. If I made them only a little more accurate, or only kind of grouping them in closer to the bullseye, but still not close to each other, these are not accurate or precise. Sorry, had that backwards. Not accurate or precise. So these are all up and not close to each other, so not close to the target. And as I go down on the image, it's closer to the target, but still not close together. So we've got no precision over here. Whereas on this side, we do have precision. Notice how both of these groupings are close together, but only one of them's on target. So this bottom corner image would indicate accuracy and precision, whereas up here it would just be precise, but notice how it's still off target, low accuracy. Now, this can actually help us. I know it's kind of a simple picture, but it helps me picture how this relates to our sources of error. So let's take this one step further and tie this into random errors versus systematic errors. So first, a general definition. A random error is something that's high sometimes, low sometimes. It bounces, it fluctuates, it's random. Whereas a systematic error is going to be something that is consistently pushing our data higher or consistently pushing our data lower. But it's a uniform effect. It always goes in the same direction. So notice how all these data points have been pushed in the same direction. So that would indicate a systematic error. Anytime basically that you have a high precision, that's going to align with systematic errors. Whereas if your precision is low, if the numbers are bouncing around, then you have random errors. And it's really important to identify the type of error when you evaluate your sources of error, because it's going to lead to correct mitigations or ways to fix your errors. you've kind of got to evaluate which types of errors are present. So let's focus on random errors first. A random error essentially occurs when the numbers are jumping around, up and down. Sometimes you read a number a little too high, sometimes you read a number a little bit too low. So these are things that are essentially able to be handled with the uncertainty being included in our calculations. Technically, to be a good random error, there should be an equal probability or an equal chance of the number being high versus the number being low. If there's more of a tendency for it to be higher, then it's got more of a systematic feel to the type of error. So technically, a good random error would have equal probability of being high or low. So when we calculate the random errors, when we go through and we use measurements and analyze our data, we have to be careful that the uncertainty is correct when we record it and correct when we propagate it through the calculations. So this is a really important how-to part of the video. When we calculate random errors, or when we show the uncertainty, this plus or minus thing I'm starting to show at the end of the numbers, we're basically showing what the chances are of having a number that's a little bit too high or too low. What would be an acceptable range that you should be able to tell reliably for the instrument that's used? So the way that we show that is actually different for two different types of instruments. So I want to first start with explaining what an analog instrument is versus what a digital instrument is. And the easiest tool for me to use as an example is actually a clock, because you're probably used to using a digital clock, one that actually tells you it's 12:52, and it actually has the numbers 1, 2, 5, 2. Real easy to read, right? An analog clock would be the old wall clock that actually has hands on it, where you have to figure out by the placement of those hands what the time is, where you're reading for yourself. A scale is another example that you've probably seen both ways. A digital scale would be something that you step on and it tells you the numbers, or you put something on a scale in chemistry class and it tells you the actual mass in grams, like in numbers. When it's giving a digital reading, that would be a digital device. An analog scale would be something like a triple beam balance, where you're moving the little weights back and forth and trying to get it to balance, similar to what they use in the doctor's office. Same thing, where they're moving the little weights back and forth, trying to get it to balance, and then reading what numbers they decided were right for the mass that was on it. So whenever you're taking your own reading, that's an analog measurement. Rulers, graduated cylinders, burettes, all fall under these analog measurements, where you have to determine the uncertainty based on the markings. A digital reading would be where the numbers are limited by what shows up on the scale. The uncertainty rules are a little bit different for each type of tool. So for an analog tool, you're going to have to determine what the smallest division is and then cut that in half. And we can tell that now because we know how precision is related to the number of decimal places that we see. So if the reading is 3.01, I know that last digit was estimated, and so it must be the 10th place where there was markings. The 10th place, 0.01. So if I cut that in half, I get 0.05. So my uncertainty is 0.05. If I had 3.1, I can tell that the ones place was my marking. And so then the uncertainty would be plus or minus. I would take the 1, cut it in half. So we would mark that as plus or minus 0.5. Now the format is important too. Notice that units occur in both places. The plus or minus goes in front of the number you determine, and then parentheses around the outside. So let me rewrite this one up here. 3.1, let's stick with milliliters, parentheses, plus or minus 0.5 milliliters. So unit, both times, plus or minus, and the parentheses around the uncertainty. But to get the number, that's the hard part, right? What is the actual uncertainty? You have to take the smallest division and cut it in half. And it is a little bit easier when you're taking the readings for yourself because you can just look at the tool instead of having to determine it by cutting back one from the estimation. Now, digital readings are much easier. Basically, you put a 1 in whatever the decimal place is for the data. So with this digital reading, the scale showed you 3.01. And if it showed you 3.00, you would record 3.00, right? You record everything that the digital screen shows. Whatever the last decimal place is, you're going to basically play matchup with your answer or with your uncertainty and put a 1 there. So if this were 3.1 grams on a digital scale, the uncertainty would be plus or minus 0.1 grams. Just playing matchup with the place value, or how many decimal places back we go. Play matchup there and just use a 1 always. So that's our digital versus our analog uncertainties. So something we want to make sure that we're doing correct every single time you record data, that we determine the uncertainty of the tool and we use that in the data. And then in Notes B, we're going to talk about how that propagates through our calculations, or how we carry that through our calculations. So very important how-to here on how to determine the uncertainty based on the tool. All right, so now that we've gone through how to kind of account for the random errors, let's finish up with random errors. They basically determine, or they're basically from the tool. They're based on the tool that's being used. So some examples here of what could cause random errors. The readability of measuring an instrument, which is essentially like how many decimal places, how close together those are, how well you're able to actually make the measurement. So that's why we're trying to represent that reliability with the uncertainty. Also fluctuating temperature, pressure, things that bounce up and down. I will warn you, you're going to see temperature and pressure again in the systematic errors. It could be either one, which is why we're going to measure controls so we can determine if it's bouncing up and down or if it's consistent. But if it's bouncing up and down, you would consider it a random error. Be careful with the idea of air currents here. 9 times out of 10, a scale is a terrible source of error, and we'll talk about why when we get to some labs that use scales. But any basic idea that's actually relevant, that the temperature or pressure is bouncing around, would constitute a random error. Also be really careful, this one's probably the trickiest on here. Insufficient data can't be human error. And in IB, we are really going to push to get enough data, because it's part of the IB rubric to actually have sufficient data and sufficient data processing. So we want to try to avoid this being a human error. But if you had sufficient processing and then realized that something else needed to have been measured or something like that, that could possibly be argued as a random error. I would avoid it. The last thing on here is a misinterpretation of a reading, and be careful again that you don't go over to the human error side. It can't be, I read it wrong, or I don't understand how a burette works. It has to be an actual reading that you couldn't quite get perfect. Like lag time would be a great example, where you can't quite tell when to stop the timer. It's kind of impossible to tell exactly when a reaction is over, for example. That would be a good example of like not quite getting the right reading, misinterpretation. So the idea here is that whenever these things are not quite perfect or a little bit fluctuating up and down, we can mitigate that with something called repeated trials. And in all IB labs, we're going to do 3 trials every time. So we want to make sure that we have sufficient data. And in order to mitigate random errors, the idea is that you need at least 3 trials to statistically or significantly affect the outcome, or to be able to mitigate these random errors. The catch is this repeated trials thing is really only a good mitigation for random errors. Repeating trials is not going to help a systematic error. The idea behind doing repeated trials is that we can then average the results. And if we average the results, especially in something that has accuracy but is a little imprecise, averaging those results helps make them more precise and accurate. It helps bring them closer together to the true value. Averaging results like these isn't going to help us at all. The average would still be in that same range, that same area that's not close to our target. So averaging is not an acceptable mitigation for systematic errors. But if you have a random error, you should definitely mention multiple trials as part of your mitigation. Now let's look at systematic errors. So systematic errors are typically in the same direction all the time, and most of the time they come from the instruments or tools that we're using or the procedure itself. Not taking things into account would be more of the idea of environmental effect. Some kind of fluctuation with the temperature would be random, but if the temperature was consistently increasing for some reason, that would be systematic. So we want to make sure that we're looking at things that are always going in the same direction. And it can be high or low, but the one source of error should have the exact same effect every time. So consistently higher, a separate source of error might make something consistently lower. The idea is it has the same effect every time, same direction every time. So we see that the systematic error here has pushed our data up consistently the same direction every time. All right, so some examples of systematic errors would be if we're losing gas consistently, unable to trap all of the gas, and it's consistently decreasing in volume. That's going to have the same effect every time. Be careful with calibration errors, because most of the time you're not calibrating your own, like you're not going to calibrate your own scale. If you are doing your own calibration, then you could use it as a systematic error. But I do think it makes a good point of if a calibration is wrong, if the initial 0 is set too high, then that would consistently create too high results all the time. So it is a good example of a systematic error, just one that you want to only use if it's relevant. Evaporation is another good one. So we're going to use a lot of solutions in our labs, and evaporation is a completely spontaneous, natural process. What that's going to do is always make your solutions become more concentrated over time. That increased concentration would have a uniform effect on your lab or on your calculations. So that would be a good systematic error. I mentioned when we looked at temperature and pressure with random errors, you would see it here again. So we want to make sure that if we do have a relevant effect, careful, it has to be relevant, of temperature or pressure, that it's actually being measured so we can determine whether it's random or systematic. My favorite here is actually this last one on calorimetry. It's probably the most relatable. The idea of calorimetry is that you can take a hot metal and put it into the styrofoam water in the styrofoam coffee cup and measure how much the temperature changes so that we can kind of reverse engineer the specific heat of the metal. Well, those calculations only work if 100% of the heat goes from the metal to the water. But that doesn't happen. There's problems with the calorimeter itself. There's also the procedural effect of moving the hot metal. Every second it's in the air, it's losing heat. So that's a consistent heat loss. So the temperature would represent the heat that the water actually absorbed, which is actually less than the metal had. So that's, again, going to have a consistent effect on our sources of error. All right, now that we've talked about different types of errors, sources of errors, I want to tie this back to the uncertainty and how that helps represent our errors. So we want to make sure that we have a really good communication of what the errors were by being really, really careful about the number of significant figures included in our measurements, the number of decimal places, or basically the numbers themselves used for uncertainty, making sure that we have that correctly representing the tools that were used. And then as we move on in Notes B, we're going to go through how that needs to be handled through calculations as well. So the idea here is that we can use these numbers to communicate the uncertainty. So there are 3 different parts to recording a measurement. Of course, you know the measurement itself. Like how many grams does the scale say? You also want to make sure that you record the unit. That unit is also going to show up in the uncertainty. So we should be pretty used to this from honors. Measurement with unit. Units are a big pet peeve of mine. You know, it's going to help solve problems if you continue your units throughout the calculation. Well, the same is going to be true for the uncertainty. We want to make sure that we're always representing the uncertainty and how that carries through our calculations as well. And that uncertainty, remember, was estimated based off the precision of the tool. So that's going to basically essentially try to mitigate or try to show what the random errors are associated with the measurement. So when we write a measurement down, let me just put an example up here. Actually, oh, no, there's not one. So let's go with that 3.1 grams plus or minus 0.1 grams with the uncertainty in parentheses. We have the measurement itself. We have the unit. And then this is the uncertainty. Well, the uncertainty includes plus or minus the actual uncertainty and the unit. So this kind of has 3 parts as well. Plus or minus the number and the unit. I want to make sure we include all that when we include uncertainty. There's another big term on here. We also want to be able to interpret what the absolute uncertainty is. And you'll see this abbreviated as AU a lot in a lot of your lab documents. So the absolute uncertainty is basically the range that we would get from this. So for example, if I can be less 0.1, I could go from 3.0 grams up to, if I could also be increased 1 or plus 0.1, I could get 3.2 grams. So the absolute uncertainty is essentially my range. How far out could I actually go and still have numbers that I think are fairly reliable? So absolute uncertainty, or AU. All right, guys, that's going to do it for Unit 1A, Notes A. The next set of notes, Unit 1A, Notes B, is going to focus on uncertainty in calculations. Probably one of the most important sets of notes as we get started in the school year. So we'll see you there.